Okay, so the first about 4 pages are a lot of theory, definitions, terms that you might have heard some of them in grade 9 technology and natural sciences, but we're just going to cover them again, and then we're going to start with the calculations. Okay. Okay, so electrical current, okay, so when we have a current, when there's a circuit, that is charge in motion. So charge moving, the little main that moves. Alright, then an electrical current can only flow if, so conditions, yes, go, pitch. If, one, there is a source of energy, so there can only be a charge, electrons moving, if there is a source of energy, something that gives you your sandwiches, like a cell or a battery or whatever. Khali, what's going on with your pants? Yeah, oh. Yeah, fixed completely. Alright, or, not or, and, so there's two conditions, and if we have a closed circuit. Okay, so if the circuit is open, then you won't have an electrical current, and if there's no source. Alright, then we are going to work in science class with conventional current direction. Conventional current, that means the thought that it's positive charges that flow, even though we know it's electrons, positive charges that flow from the positive pole of the battery through the circuit to the negative pole of the battery. So we go from positive to negative. Okay, and in this diagram below, I show you there's the positive side of the battery or the cell, and conventional current goes from positive to negative. Okay, even though we know actually in real life it's electrons that flow, the whole concept, the whole ideas, the whole ammeters, voltmeters, everything is set up for conventional current direction. Okay, so in here you need to know the following symbols. You need to know what a switch looks like. Yes, how to draw it. You need to know a battery. You need to know a light bulb. Okay, so light bulb is an X. I'm going to move over to the symbols here on the right hand side. So there we have a lamp or a light bulb, a voltmeter, an ammeter. Okay, does it look familiar? You've seen them last year? Yes. Then a resistor. Okay, then the first thing there that's new is a variable resistor. I think that's new. Okay, so Valentine's Day was just like a month ago, right? And Khali wanted to impress the special person in his life. Okay, so first of all, he put on some music. Okay, can he blast the music? No, what does he do? Jazz. Okay, I'm not asking what type of music. Blast means must be soft. So what does he do? He changes the volume button, right? That when you change it, that is a variable resistor. You can make it very loud or you can make it very soft. So that turning. Then he wanted to have a nice atmosphere. Must the lights be bright? No. It should have been candles because load shedding. But let's say there was no load shedding. Then he dims the light. Have you seen those lights where you press the button or you turn it and then the lights go soft a bit? Yes, so he dims the lights a bit. So anything that you changes how high or low, bright or soft, or if we have this fan, then it can change. Must it blow very hard or 2, 3, 0, whatever. This is called a variable resistor. So we can change the strength or the size or the magnitude of the resistor. Okay, so how do we show that? It is the same as a resistor block, and then it has just an arrow through it. Okay, If you have old textbooks or you have extra classes at somewhere that's an older person, an older way of showing it was doing it like this. Okay, so they put an arrow like over like that, or like this. Okay, yes, you've seen that? Yeah. Alright, but in science class now we use this blocks. Alright. Then a motor there you do not need to know. Okay, you do not need to know, just for interest's sake, that a motor is like a generator, or let's say you, like in here, is plugged to a source, but in here is a motor that turns. Alright, source, motor that turns. Okay, right, then the next concept there is electrical potential difference. Electrical potential difference. Okay, definition. Something in a block is a definition. Says there. What is that? It is the energy transferred. Then there's the word per. What did I say about the word per? It means divide. It means divide. The energy transferred per unit electric charge flowing through a circuit. Okay. So, electrical potential difference, and I told you, you must think of it, potential difference as volts, right? Potential difference, your volts. And in my little story, what did I say was that volts? Your sandwiches, your energy. Alright, so your volts is actually how many, hashtag is how many energy per man. Okay, so how many energy does one man carry? We said 3 volts, so each little man carried 3 sandwiches. Yes? Okay, so the scientific way of saying that is the energy transferred. How much energy does the man walk with? The energy transferred divided by electrical charge per little man walking. Okay, sharp? So the formula that goes with that is this formula, and it will be on your data sheet. Okay, now V stands for your potential difference or your volts. Q stands for your charge in Coulomb. We did a whole chapter on charge. Then W stands for the work done. Now, ma'am, we just spoke about energy. Now you speak about work done. Energy work done, and that is measured in joules. What is energy measured in? Joules. All right. If you now, now you will see my very unhealthy habit. So if I check the energy here, who do I trust? That energy. What is it measured in there? Kilojoules. So energy is measured in joules. Work done is measured in joules. Okay, so energy and work done, you can think of it as the same thing. So work done is the same as energy. Yes?
How do you tell apart watts? Is it the same thing?
Oh, no, watts is power is measured in watts.
Did you say W? For like shorts?
You can, yes. But this W is work done measured in joules. It is confusing. Okay, so that formula you need to know that V stands for your volts, W stands for your work done or your energy in joules, and Q is the charge. Alright, so we're going to do a calculation with that a bit later on. Then it says, in cells, stored chemical energy. So in your cells, in your battery, you have chemicals. Stored chemical energy is converted to electrical energy that enables charges to move through the circuit. So that chemicals give the charges electrical energy that they move. So you need to know the conversion. You need to know. Let's vote. You need another color highlighter. Yes, I'm not born yesterday, Khali. Just switch with him then. You have 4 colors in front of you. Alright, okay. So chemical energy is converted to electrical energy. You need to know that conversion. And that enables charges to move. What does the word enable mean? Allows, ne? He already gave the answer. Yes. Alright. Then, in this circuit, charges experiences resistance. Okay. So, as you go through a circuit, there's resistance. Why? Because of collisions with particles. Collisions is when they collide, when there's a, like a, I don't want to say a fight. What are you busy with? Yes. All right. And because there's collision with particles, and then because there's collision, the electrical energy is converted into heat energy. Okay. So when you clap your hands a lot, right? After a while, you will feel your hands becomes warm. All right. So when there's collisions, it changes into heat energy. Those of you that plays rugby, when there's a lot of collisions, then you become warm, né? And you sweat. Yes? You don't know. Or when you play soccer and you fake an injury and you collide with the ground. You play cricket?
Yes.
For the school?
Yes.
Oh, I did not know that. Why are you all laughing? Is it not true? Is it true?
He ended, man. He worked very hard.
He ended.
Yes, he earned it.
Well, earned it. Well, all right.
He worked very hard.
That's good. All right. Then potential difference. Okay. So there we have the volts. Only exists where energy is added or where energy is used. So you can only and that's what we had yesterday with our practical that we did on the board. When the switch was closed, no energy was used. We said it was 3 volts and 3 volts. 3 minus 3 is 0. So because there was no energy used and no energy given, there was no potential difference. Alright? But when you have over a cell where it gives energy or over a resistor where it uses energy, then you have potential difference. Okay. Then potential difference is measured between 2 points with a voltmeter. Okay, connected in parallel. What does parallel mean? No. Yeah, over each other or not next to each other, over each other, right? So like we have here, the voltmeter is over the resistor. It's not, I don't have a voltmeter there. It's not next to the resistor. It's over the resistor. Okay. Then, when connecting voltmeters, observe the polarity. We said the black is negative, the red is positive. Right? And then, use larger scales first and then change to a smaller scale. Why? Okay, so that is just basic maths. Okay? So what I'm going to do is I'm going to send this voltmeter around. Okay, and then I want you to see that there is 1 black socket and 3 red sockets. Okay, so the black will always go here. Then the red will have a choice. Does it go to 3 volts, 10 volts, or 15 volts? Okay, this does not give volts. Does not give energy. It just measures. This is meant to share. Just check. Alright, and then I want you to see on here, there's 3 scales. Alright, there is on this side 3, 15, and 10. So it depends where you put this in, where does it go, what's its maximum. Now it says there, when you use a voltmeter, always starts with the bigger scale, 15 volts, and then move to a smaller scale. Okay, now why is that? Let's say we have a kitchen scale that you measure off your flour and your what, you know, a small scale? Yes? Some of you look like you don't know.
Then, why did they tell us this about the coming of 11 o'clock?
The message was only given to Tomahole schools.
So us, we didn't.
So we were not invited. And then we got invited a bit late.
So now, now they inconvenience us because
I know it inconvenienced me as well. But that is life, eh? What?
the exercise don't come and fetch us.
So again, the text.
The exercise is not going to come and fetch us.
Then you walk.
To Fairford.
To 3 Elephant. Then you can stay at school until 1 o'clock. Alright, so this is not a kitchen scale, but a kitchen scale can look like this. Is a small scale. This scale can only go till 220 grams. That is the maximum that this scale can weigh. Okay, why do I have such a small scale? Because we measure of very, very small quantities of chemicals, powders, whatever. So I want it to be very accurate. If this one goes until, I think, 1 decimal. Say again? Yes. I bought it last year. It's very expensive.
Last year.
Can we just eat now?
Yeah. Alright, so let's say we have this scale and we have a normal scale, a bathroom scale that you climb on. If you want to measure your weight, alright, which scale will you use? The bathroom scale. Not this scale. If you step on it, you break it. Okay? Now, when you're busy with a current, can you see how big the current is? No, you don't know. Alright? So that is why you start with the biggest scale first, because you're scared you will break the smaller scale. Start with the biggest scale and then you say, alright, let's say your reading is very small and you can't see on that scale. Then you go down a bit, one smaller, and then you go down one smaller. Okay, so let's say I want to measure off 0.1 grams of a powder. Okay, can I use a bathroom scale? No, it won't move at all. Okay, and then say, okay, that scale does not work, now we'll move to a smaller one. Alright, so you know what's good manners in science. Okay? Right. Then a voltmeter has a very high resistance. Why? So that no current passes through it. So we said yesterday that when you get here, you can't pass through Miss Fouchier. Alright? Because the resistance is too high, you can only pass through the resistor. Okay. So what I want to check here is just again what we did yesterday. The long one is positive, the short one is negative. Now here the little man walks with 24 sandwiches, 24 volts, 24 sandwiches, right? And he needs to say, right, I'm going to split my day into 2. I have, I don't know, science and Afrikaans. Okay, which one gives more resistance, science or Afrikaans? Really, you enjoy Afrikaans?
No. Yes.
Okay, who teaches you Afrikaans? All right, so you are going to divide your sandwiches into 2. Your sandwiches, your 24, you're going to divide into 2. Okay, can you see you don't have a choice into which subject you go to? You're not going to say, I'm only going to go to science, but not Afrikaans. You need to go through both. So we can see the current everywhere is the same. Okay, now, before you enter a science, how many sandwiches do you have? 24. Now I'm telling you, after science, you have, what's 24? Nee, wait net. You have 8 sandwiches left. Yes.
Why is this second going like this?
Because it always goes from positive to negative. It depends how the cells are connected. What is this? 16. What is 24 minus 16? It's 8, ne? Yes. Okay. So what is the potential difference there? 16, right? Okay, because it's the difference between 24 and 8 gives us 16. So of your 24 sandwiches, you ate 16 at science because the difficulty is higher. 16 sandwiches, imagine. All right. Then before Afrikaans, how many sandwiches do you have? After Afrikaans? 0, because after Afrikaans you go directly home. So you ate 8 sandwiches there. So what is 16 plus 8? 24. All right. Next page. Okay. Then we did this practical yesterday. Then I was busy with cells in parallel. We saw that cells in parallel last longer. And we said that it's like you have 1,000 sandwiches for life. And you can either choose, do you take 4.5 sandwiches every day or do you take 1 sandwich every day? Obviously, if you take 4.5, you'll have lots of energy for the day, but you will run out of energy quickly. But if you take only 1.5 a day, you'll have less energy, but you will last a lot longer. All right. Bukamuso, what's wrong? What's going on? Wow. You can borrow from Khali as well. There's lots. All right. Thank you, Tatu. Right. Then the EMF, and I'm going to get to what the EMF just now. The EMF of a battery made up of cells in parallel is the same as the EMF of a single cell. And we saw that in our practical. Even if we have 2 cells, it's just as if you have 1 cell. Because we said it's like you either get your sandwiches from your one parent or the other parent. I just highlighted this. The rest were highlighted yesterday. You highlighted nothing. Well, he highlighted. That's his own fault. All right. So, what is EMF? That is the definition. EMF it stands for electric motoric force. Electric motoric force or electrical motoric force. Motoric, so like a motor. Motoric force. Huh? Well, it depends how you pronounce it. I don't know. All right. So the definition there is the work done per unit charge by the source, by the thing that gives energy. So it's the same as the potential difference definition, but now it's just what the source gives. Say again? Per means divide, yes. Right. Then this EMF, this potential difference, is equal to the potential difference measured across the terminals of the battery. What is terminals? The ends, the sides. The terminals of the battery when no charges are flowing through the circuit. So when your circuit is open and you measure the volts over the sides of the battery, what volts do you get? Okay. Then what is terminal potential difference? That is the voltage measured across the terminals of the battery when charge is flowing through the circuit. So EMF is when there's no charge going through it, and terminal potential difference is when charge are flowing through it. But ma'am, isn't the same thing? You'll sing grade 12, it's not the same thing. Huh? If you get there. When you get there. All right. Then we're going to go to current strength. Current. I told you the first few pages is a lot of theory. It's a bit boring. We're going to get to the calculations. That's nice. Okay. Current strength. Current. The symbol for that is a capital I. And the definition is the rate of flow of charge. Now, what does the word rate refer to? Did I start with my questions today? Yes, Khali. So now it's about so. Rate. What does the word rate refer to? Amount of what? Oh, yes. The rate at which the grade 10 Ds came to my class today was shocking. No. It was only you that was early. The rest.
Professionalism.
No. The rate at which the learners will leave the school at 11 o'clock will be triple speed, right? So rate refers to the speed, okay, or divided by time. So rate means divide by time. Okay. So the rate of flow of charge, so the current is how many charges pass a point per second. Okay, so I told you the current is like, the current we measure with an ammeter, right? And that was like, I told you it was like register period, or like that old bell when you enter a shop. Bing, 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 bing. So how many charges pass a point per second? Do we still have shops like that?
Yes.
At the pharmacy. I think also at that craft shop. Or also the Manswinkel. I've never been into that shop.
And those old shops, antique shops.
Well, yeah. What uniform? Remember, I don't come from Parijs. I come from the Western Cape. I came here 4 years ago. I'm not from here. No, I come from Worcester. Huh?
So you came here to show the first aid ladies.
Is that you or me?
You man, you came to show.
No, I came here because I love my husband. Huh? No, we're not in America, eh? Worcester. Yes. Bell. Sorry, 2 L's. Bell. Oh. 12. Alright, so what is electrical current strength? Another way of thinking about it. It is the amount of charge, like how many men flow past a point per second. You know, sometimes there's people that sit next to the road in a chair with like a vest on and with a booklet, and then they count how many cars pass that road. Have you seen that before? Why do people do that? They need information to know, all right, is this a very high traffic road? Do they need to make the roads bigger? Do they need to make another path through here? Blah, blah, blah. So they count how many cars pass this stop per hour, per day, per whatever. Same idea. Here is how many charges pass the point per second. Okay, so a million, trillion, we will see. Okay, then we measure current strength in amperes or amperes. Then it's measured with an ammeter connected in series. Because why must it be in series? Like it must be inside, not over. Not like the voltmeter, like that over. It must be in because we want you to pass that point. Okay, so it's like a scanner. Beep, 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 beep. All right. So it must be in series. Remember, the red is always connected to the positive side. Black is connected to the negative pole of the battery. Then always use the larger scale first. Otherwise, you'll break the ammeter. Ammeter has a very low resistance. I told you register. You don't need a lot of sandwiches for register. You just pass through it. And it's connected in series. Okay. Then we have electrical charge. Electrical charge Q. Okay. Now the definition here is not the definition of electrical charge. The definition here is the definition of 1 coulomb. So they can ask, what is 1 coulomb of charge? What does that represent? So that's a definition of 1 coulomb. Okay, what is 1 coulomb of charge? Okay, so if we have 1 coulomb of charge, it passes any cross section, so any part in a conductor in 1 second if the current is 1 ampere. Okay, so this is a very weird definition, but I see that they do ask it. I don't know why, but they love to ask it. So you just need to know if it says a charge, the current is 1 ampere, then it's 1 coulomb of charge in 1 second. Or 1 coulomb of charge in past a point in 1 second if the current is 1 ampere. Okay, we know that we measure charge in coulomb. And then another definition. Another definition formula. Alright. So Q is the charge in coulomb that we did a whole chapter on. Then I is that current that we just spoke about in amperes. And T is the time in seconds. Okay. Now go to your data sheet, please. Alright. Okay, so on page 27 of your data sheet pages. Open your data sheet.
27.
Page 27, yes. Okay, then you can see here all the way at the bottom is the electricity chapter formulas. Can you see that both formulas that we have discussed now is on there? On the right corner there at the bottom is V is W over Q. We're going to look at that formula in a moment. And then there's a formula Q at the top. Q is equal to I times delta T. Okay, so those two formulas are on there. The other formulas we'll get to. Those two formulas will be on there.
This one, and this one.
Yes.
But this one
No, we're going to get to those formulas a bit later on.
not it says in the next case.
No, later in this chapter. Alright. Now, I put this triangle in here because I think you did this triangle last year. Did you use triangles last year? In technology? Water boy? You just give it.
Yeah, scared of him because he's smart.
Wait.
Alright. Now you won't get a formula. You won't get a formula or a triangle like this in the test room. Okay, this is just to remind you, listen, you've done triangles like this before. Okay, but you'll get this formula. Now let's see how do we apply this formula. It says a light bulb requires 250 milliamperes to burn brightly. Okay, so it gives you 250 milliamperes. Total. What do they give us there? What symbol goes with milliamperes? Say again? No, there is amperes. What goes there? I. Then, Kamu, do we work in milliamperes? No, we work in amperes. How do we go from milli to normal? Millimeters to meters? Positive or negative? Khali, stop it. -3. Okay. What quantity of charge? What are they asking us there? Let me start. What are they asking us there? Quantity of charge. Say again. Yo, what's the symbol that goes with that? Q. What charge has moved through the bulb if it has been burning for, and then they give us 10 minutes. Hope, what goes with minutes? Huh? Hope? What goes with, say again? time. Alright, then Bukamuso, do we work in minutes? What do we work in? How do we go from minutes to seconds? By what? By what? Bukamuso, in science class, 1 minute feels like a lifetime. 1 minute is how many seconds? Okay, so what are you going to do to go from minutes to seconds? By? No. It's the answer is going to be 600. 60 times 10. Yes.
Does the T for time always have to be lowercase?
Yes. Low, yeah. The capital T is that period in waves. Capital T. Yes? Yes? Alright, so we write down the formula. Thank you, Sia. Q is I times T. The Q we want to get, the current is 250 times 10 to the power negative 3. And the time is 10 times 60. And Miyakano is on it. Oh, Masho? It doesn't have to be, but it can be. I now understand that you come from another province.
You understand what? You understand what? I come from what?
Another world.
I come from Mars. I'm an extraterrestrial
Body.
being. Not being. And I come to study.
Kamu? Kamu. Kumo, take out your calculator. Bukumu, show your calculator out. Yes. 150 what? 150?
Are you sure?
They start to? So you have 1.5 times 10 to the power of 2. Same answer. Same thing. Right. Then the last bit of work for today, resistance. Okay, the definition there. Resistance is the ratio of potential difference across a conductor to the current in the resistor. Okay, now when we say ratio, we can also say the word relationship, or we can say the word or the idea of a fraction. So when we have a ratio, so I can ask in this class, what is the ratio of boys to girls? Okay, then how many boys do we have? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 boys, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9. No, 6, 7, 8, 12. We have 12 ladies and we have 10 gentlemen. Alright? So what's the ratio of, if we say boys to girls, then it's going to be 10 over 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. But I'm not a girl, I'm a woman.
Woman.
Alright. Come. Come. Sorry. Alright. then it's 12 to 10. Okay? So there's 1.2 girls for every one boy in this class. Yes?
Why don't we do it with the dot dot?
We can do it with the dot dot, but I want you to just see it like this as well. Okay, because I know the dot dot you've seen in your life before. Dots. Alright, so if we say what is the ratio of potential difference to the current, okay, then it's the potential difference to the current. And that gives us the resistance. Now that formula you've seen, yes? Quickly look on your data sheet. Is that formula on your data sheet?
No, it's not. You have to like it.
It is not on your data sheet. So this is a formula that you have to go study, memorize, off by heart. So that means you need to study it, memorize it. For tests and exams, yes. Next term, yes. Alright. Then R is the resistance in ohms. It looks like a shoe hoof. Shoe. A horse hoof. Horseshoe. Alright. Then V is the potential difference in volts. And I is the current in amperes. Okay. Then you also need to know that resistance is the opposition to flow of an electrical current. Okay. Now that is like what we have at the fall down. Alright. Why is our river not always flowing fully like it is flowing now? Why is it not always? Why is it sometimes flowing very slowly?
They close
Okay. They close what?
the gate.
They close the gates at the boat. Okay? So they give resistance. When they open all of the gates, like they did now with the floods, then the river just flows very roughly, and what happens to the houses and the buildings and the stuff? But it's taken away. Right? So do we need to add resistance sometimes? Yes. To cause the current not to break your appliances. So from our clouds, we get about 220, 240 volts from here. But our appliances can't handle 220 volts. Okay, it will burst. So in here and in there, we have resistors purposely put in there to control the current. Okay. Say again?
So then how does
Yes, also in your houses.
The transformer is the resistance.
Yes.
so then how does it work in charges?
In charges, there's a big adapter that changes it. But it also changes the type of current. We go from alternating current to direct current. We're going to get to that in
The
relief.
fast charger, the immediate is the fast charger.
Yeah. I don't know. I don't know what it looks like inside. Yes.
Listen to me, listen.
What does she say?
She says we have transformers in the house.
She said that you
Now, you say so, then transformer in the house.
There's
Volts, man.
yeah, but it also transforms and regulates your current, your electricity in your house. That's why you can't cheat the electricity and connect it directly from the pole to your house safely. Then you might, yes, you might do something. All right, then, and there are 4 factors that influences the resistance of the flow of electricity. Okay, so 4 factors that influences the resistor. 1 is the length, 2 is the thickness, 4 is the temperature, 3 is temperature, and 4 is the type of metal. Okay, so I want to discuss them quickly. First of all, the length of the conductor. Now let's see, if the conductor is very short, then the charges have a very short path that they can flow through. If the conductor is very long, then it is a long path that they have to flow through. So when do you think the resistance will be more, with a short or a long conductor?
Sure.
When will the resistance be more?
Sure.
Not the current, the resistance. Long, because then they have lots of space to collide with one another and become very hard to pull everything. Right? So the longer the conductor, the higher the resistance. Then the second one there is, let's want to look at the third one. Third one is temperature. When you make, say your cell phone or your laptop or your whatever, or your computer, when that becomes very warm, does it still work nicely?
No.
Now then you stop to just put it down, put it off, put it down, blah blah blah, right? So what happens is the warmer the conductor becomes, the higher the temperature, the higher the resistance, the more difficult it is for the charges to pass through. Okay, common sense. Then the last one is the type of material. If the material is very soft, then the charges can go through it quickly, like copper. Right? So we have copper wires. Yes? But if the material is very hard, so you can't bend it or whatever, like this, if the material is very, very hard, then it will take longer for the charges to pass through because the resistance is higher. Then the last one, the fourth one, is, the second one is the thickness. Alright, now, some of you have never attended a rugby match at school, but maybe you've attended a match in the location or soccer match or anything like that. Now, before your team runs onto the field, right, what do the supporters sometimes do? They make a little tunnel, right? A tunnel kick. Good. Now, let's say this is the tunnel, right? And the rugby men who wants to run through each get up there, woo, go Paris. Okay, now if I make the tunnel like this, so it's very thin, will the rugby players be move free? No, they'll be like, we will collide with one another, it will be very difficult. When I give them a lot of space, so I make it a bit thicker, the part, then they can easily run. Okay, so that one is a little thicker. So if the conductor is very thin, the wire is very thin, then the resistance is too much. There's no space for them to pass through. If the wire is very thick, then they can easily pass through because there's a lot of space. Sharp? Okay, we are done for the day.
How can you like?